We really should do, I didn't ask you guys to fix the code, but we really should go ahead and free array 1 here. And if we had some size for array 1, imagine if we have like some int star SA1 or something like that, int SA2. If I had that SAR1 is equal to 10 here, and SAR2 is equal to 20 here, this wasn't inside the code. It wasn't necessary that you do this, and it wasn't even going to be a memory problem. It's just something useful so that way when you're working with your code, you know the size of your array. When you free the memory, you should probably say something like the size of array 1 is equal to 0, because like there's nothing stored there. And then when you update this, you should say the size of array 1 is now equal to the size of array 2. And it just like this would help you, like if you're trying to like figure out what's going wrong in your code, you'll be like, okay, so what's the size of array 1? You'll see it's size 20. Maybe that's a good thing, maybe that's a bad thing. But hopefully that could help you out. So this is like some minor edits that you could do to help you understand what's going on in your code. And this is all legal. Is there anything else that you guys noticed? Yeah?
You define array 1 and array 2 as the size of int star.
Yeah. So this is something that not many people would have caught. And a lot of people were actually doing the reverse on the test. I had it correct on the test. This isn't supposed to be star here. A lot of people were saying it needed to be star there, and I wanted you guys to be aware that no, it doesn't actually want to be star. The number of stars that's here is always going to be one more than the number of stars that are over here. Or at least it should always be that case. So this is like a few minor issues that people had on the exam. There's other things that I can go into, but I don't think any of them are as important as, or they don't like really strongly relate to what we're going to be going over today's material. And today's material is going to be more dynamic memory. And so if you had issues with this is the problem, you might have issues on these type of things we're going to be doing later in class. And so you need to like work really hard to go ahead and figure out everything I'm saying, ask questions. You're confused, you know, don't be afraid to go ahead and ask someone else, preferably after class, ask me. We can go ahead and work through these things. So, questions?
So, if you were to copy the stuff in array 2, 20 and power, into array 1 into the for loop, that would be a problem because you would be writing into memory that you didn't allocate for array 1, right?
So, if we wanted to just resize array 1, we could have done the realloc. You shouldn't use a for loop plus calloc on this array because this is not a two-dimensional array. So if you wanted to copy the memory over though, you could like reallocate, or you could allocate, you could use, so after we create array 1, we could have calloc array 1 to go ahead and create a new array and use the for loop to copy all the values in, and then we would have 2 copies of it, and then that would have maybe made more sense, because having 2 things point to the same value can be dangerous in code. Sorry. Okay.
Maybe I worry. So on the test, isn't what happened is like there's a for loop that copied what was in array 2
Yeah.
into array 1, and then it would rewrite, like you'd be rewriting memory that you didn't allocate array 1, right?
Yeah, so we were going out of bounds was one of the issues that was in the exam. Yeah, so if you notice that, that was worth some points. Another thing that we were doing was that we were not freeing array 2. Another thing we were doing was we were freeing static memory. And another thing we were doing, we were, what was the last one? Oh, we were setting a static memory to a pointer, and that's it. That's not allowed. So, yeah. All right, question.
Is the reason why you're not freeing array 2 is because you're setting array 1 to array 2?
Yeah, so because we're setting array 1 to array 2, we don't want to do it. And so like some issue that people will run into when they're doing code, and this is something that you need to be aware of, is some people will do array 1, this is like a new thing. So int star array 1, I'm going to make my life a little bit easier. I'm going to call this B. So I'll do array is equal to int star calloc 10 size of int. And now what they'll do is they'll do b is equal to array, and then we'll go like later, I should say, so dot dot dot. Then they'll go free r is equal to null to prevent dangling pointers, and then they'll say free b b is equal to null to write dangling pointers. So the issue with doing this segment of code, does someone want to point this out actually? Yeah?
The data is already freed.
Yeah, so we already have freed the array. So what happens is we have some array here, a box, that's pointing to some section of memory. And then we have some b, and then we have it point to the same section of memory. And then what we do is we say, all right, we're going to free this memory. And so this memory has now been freed. And now what we do is we say, all right, you're going to go ahead and point to null now. And that's going to go ahead and prevent any issue that we might have with dereferencing null. But then the issue is we now say, hey, b, you're pointing to some value. Why don't you go ahead and free whatever you're pointing to? b's pointer hasn't changed. b is not pointing to null right now. And because of that, we're going to go ahead and free some section of memory that's already been freed. And this is going to be a double free. That's a big issue. Why did I need a semicolon? All right. So double free is not good. That's bad. Not good is bad. All right.
I have a question.
Yeah.
If you called it something else instead of a double free, or you pointed that it wasn't an issue, you get half points?
Depends on how serious it is. Like if I understood where you're coming from, then I gave you the points. If I couldn't really understand, I might have given you partial credit. But I try to use my best judgment on that. Like sometimes people are just emphasizing every line. Like this is a problem, this is a problem, this is a problem. That's like, guys, I know I write bad code, but it's not that bad. On people like that, I tended not to be very lenient, obviously. But people that had very few lines, I tried to figure out what the reasoning was. And if it was again, I understood where they're coming from, and it seemed like that was a reasonable explanation, I tried to give them points for it, even if they didn't word it 100% correct. You'll even see sometimes when it's written out for grading, I'll be like, okay, ... This isn't 100% the reasoning why, but I'll give you the points anyways. I wanted to have them back today. I'm really sorry, but it might not be until next week potentially. I'm gonna hopefully have them back Wednesday. It's just unfortunately, I had another test to grade as well at the same time because there was 2 exams last week. Hopefully, everything will be ready though soon. We have actually a majority of the things done. I think the last time I talked to someone, we were last time I checked, it was 90% done. So there's just this last 10%. Unfortunately, it's on me. And it's because I decided to take a majority of the exams, a majority of the questions on the exam to grade, a sizable chunk anyways, and that's causing me to be slow. All right, but yeah, what? Assignment 1, I'm not grading any of those, so that's not my fault. I'll check to see what the progress is. I actually got an update from 2 TAs today, because I sent them emails hey, what's going on? 2 of them were oh, I finished my thing. It's great. I'm waiting to find out when that last TA is done, and when it's done, I'll be able to publish everything. But so far, I don't know if that's going to happen. I'm writing a script to go ahead and replace him. That's terrible. All right. Well, hopefully I'll be able to give you guys temporary grades, and then I'll probably update them when I go through them by 2. What's up?
What if I already wrote a script that replaces them 4 times 2?
That's cool. We can talk about that offline. So what we're going to be going over today is a special type of dynamic memory. And so the type of memory that we're going to be going over today was known as linked memory. And I know that linked memory sounds really weird to you guys. I feel like memory already has links in it, probably is what you want to say, but we'll go ahead and explain that in a little bit. Question? Okay.
For assignment 3, I looked at it and I saw that it was linked memory.
Okay, so if it says binary search in there, I uploaded the grading rubric to not say binary search anymore. Yeah, so that was oops. I meant to actually send an announcement about that. I guess I didn't get around to doing that. I'm really sorry. There should be an updated grading, or not grading criteria, but there should be an updated problem statement. And then in the problem statement it says if you don't use linked memory instead of if you don't use binary search. So yeah, I guess I saved multiple versions and I just uploaded the wrong one. And what's even worse is when I closed my Windows and my Word, because it's what I used to edit all my things, and it's oh, we're recovering a document. I'm it's probably just some garbage, and I deleted it. So I'm actually back a couple versions. That's just not good. But anyways, yeah, it should be more up to date. All right, so linked memory. So when we've been doing dynamic memory, what we're using is these pointers to reference other things, right? We have some box that points to some section of memory. And potentially this is like a 2D array. So imagine this is array star star, or sorry, maybe this is like int star star array. Then each one of these boxes that this is pointing to, because this is like an array, is pointing to another box. And then inside these boxes we have memory, like 1, 2, 3, and maybe we have 4, 8, and they don't have to be the same size. 11, 10, and some of them can even point to just null if we really wanted to. So this is kind of what memory looks like if you decided to draw it out pictorially. It's very fun to draw. There's a lot of arrows going everywhere. And so when I say linked memory, you guys are probably already like, we've worked with this before, why are we going over this again? And the reason why is because you haven't really gone over it the way that it's like at its final form almost. So one thing that's really interesting about this is that, yeah, we go ahead and link down one direction and then we link down two, but then once we link two directions, we can't link any further, right? Is there any way I could go ahead and create like a third link that I can follow down? Like maybe like just giving a trail with breadcrumbs? Like how could I create a third link?
A third.
Making another array? So I could make another array. So like instead of using array star star, if I wanted to create another link, instead of doing int star star, like the int star has only one link, right? And so the int star star has two links because they go 1 and then 2. So if I wanted to create another link, I would actually want to do int star star star. And then what I could do, yeah, you guys are already probably really uncomfortable about this. I could have like this arrow that points to something, and then this points to something else. And then this thing points to something else, which will be like some set of numbers. Which will be like really crazy. And like this could like branch out like in a huge fashion. It would be really awesome. And you'd probably get something that looks almost like a pyramid or something. I don't know what pyramids look like anymore. So don't ask me to draw them. But one thing that's really interesting as well with these links is we could also get some really weird behavior where they could potentially branch out and converge. Like you could potentially have, like imagine like a really weird case where this is like pointing to some guy here, maybe this is 10, and maybe this guy points over here. You'd have like this link potentially pointing over there. Like that'd be totally kosher and probably a little disgusting to like try to implement. But this is like the type of behavior that I kind of want to get to. I want to get to the point though where we're going to have an arbitrary number of links. And the thing is, if I have an arbitrary number of links, like amount of indirection I can have, it would be a little bit weird to do that. And you might also be like, well, why would you want to have an arbitrary number of links anyways? Like, what's the point? Why can't we just use a regular array? So why would we want this linked data structure over just the conventional array that's a fixed size? Actually, no. Yeah, sadly, not really. I'm going to go over why in a moment. So if we want to go ahead and create a large fixed size arrays, so what's going to happen is I'm going to have to find a section memory. Like my goal is to find a section in the heap for the allocation. That's like going to be the task of the thing that's running this, whatever environment you're running this on. It's going to have to be able to find out where to put this memory such that we can go ahead and use it. But the issue is, if you have if you've already used some of the heap, you could potentially have done something really weird. Imagine in the heap, which the heap is like kind of like this. It's a stack-like structure, which doesn't make any sense for you guys right now. But the idea is it grows from the bottom up. And basically you put some memory in here and you can eventually free it. Well, if you put like a whole bunch of memory in here, like of these different block sizes, and so this is like block 1, block 2, block 3, and block 4, block 5. Imagine we filled this up really nicely, and then what we decided to do is we decided to free up some memory so that way we could allocate this large array. And we're like, well, I don't really know what memory is in the order within the array. I just know that I don't need like 1, 3, and 5 or any odd number anymore. So I can go ahead and free this memory here, and this memory here, and this memory here. And now the problem the environment's going to have when it's trying to run this code and it's trying to find the memory or the location to put your memory, is that it might not be able to fit it anywhere inside this heap. And the reason why is because it might need to stick something that's like this big. And it's like, I can't actually fit that, well, it might be like a little bit wider, obviously. Dynamic memory is weird. All right, I'm going to erase that one. Here we go. So I want to stick this in here somewhere, so new block. But the issue is I can't actually stick the new block anywhere. Now, what would be nice is if I could split this new block into sections. I could very easily stick it into this heap. I could go ahead and stick that part down there. I could stick this part over here. Maybe I could stick some part over here. Maybe I could go ahead and stick this like up here even. But the thing is, like, the program doesn't implicitly do that. It's very stupid. And it tries to go ahead and stick things that don't fit in potentially. And if it fails to find out where this new block can go, it will actually go ahead and return null. It'll be like, hey, I wasn't able to allocate your array, even though it's like, well, I have like 50% utilization, and this is only 10% of my array size. But it's like, if you fragmented your memory out, you might not actually be able to find a location for this memory. And so that's going to be a problem. And so what we decided to do is we decided to, as computer scientists, make this horrible for ourselves. And we decided to go ahead and find a way to split this memory somehow. And we do so in the worst way possible. So what we do in this structure, imagine we need to go ahead and create basically this large array, but we can't actually create the array completely. We'll go ahead and create the array one element at a time. And so you can imagine if I want to create the original array of 7, 3, 4, 2, 1, 5, 5, 9. So if I can't stick this in memory, instead, hopefully I can go ahead and create a slightly smaller array that I'll go ahead and then say, hey, the next position in the array is going to be over here. And so we'll go ahead and try to break it up ourselves, and hopefully it won't be in a terrible way. Now, there's various levels of granularity you can go ahead and break this array down into. The most obvious one would be to split it element by element, and that's kind of what ends up being the final solution in this case. But we could also potentially group them up as well. So let's go ahead and try to just group them up initially. So we'll go ahead and make this group 1, we'll make this group 2, and then we'll make this group 3. And now what we want to do is we want to have these guys basically pointing to each other, or like from group 1 we can get to group 2 so that we can find the element if it's not in group 1. And then from group 3, we can get, from group 2 we can get to group 3 if the element is not in group 3 either. So you can imagine that we have some sort of memory that looks like the following. We have 7, 3, and 4 here, and then this will go ahead and point to a new section of memory that has 2, 1, and 5 here, and then this will go ahead and point to another section that's 5, 9, and maybe there's like nothing here, and then this will go ahead and point to null to signify this is the end of the array. And so this is what's known as a linked data structure. It's very interesting looking, hopefully. If you've seen this before, then you've probably taken CS1 before, in which case I'm sorry. Or you've seen a really nice tutorial, because this is kind of something that you'll never be exposed to in Intro to C. Did anyone see this in Intro to C? Raise your hand. Wow, okay, cool. So you had some pretty good Intro to C teachers then. I'm sorry for bashing on them if I've done so in the past. Is there anyone that's unclear of what I'm trying to do here, just pictorially? I won't even go over the code immediately. Yeah, so what's up? Yep. So the idea of linked memory, though, is it doesn't have to be confined to just a linked list. It can also be different types of linked data structures. So if you've been exposed to linked lists before, have you been exposed to something called a binary search tree or a binary tree? So that's also a type of linked data structure that we're going to be covering later. We don't know about it right now, but that is something that we can end up using. Another type of linked data structure, technically it's not a linked data structure, but stacks and queues can be implemented using linked data structures. So yeah, you can do it however you want. That's the awesome part about linked memory, is that you can go ahead and create the links however you want, just as long as inside the data structure, which I'm going to get to in a moment, is you have the ability to point to another data structure of the same type. So it doesn't even actually have to be a data structure of the same type. You could actually have alternating data structure types, but that's like probably more advanced than what this course is going to be going into. For this course, we're going to be going over basically one type of data structure that points to itself. So yeah, let's go ahead and talk about what that can look like. Yeah. So the reason why is because if you're trying to run code and your code isn't able to like stick an allocated section of memory anywhere inside your heap, then this fractioned off guide can make it so that way you can find sections. So hypothetically, if we couldn't make an array of size 10, but we can make an array of size 4, an array of size 4, an array of size 4, then we could have gone ahead and made those three, stuck our values in, and then stored them into our heap somehow. So this helps when your memory is what's known as fragmented. Is anyone old enough here to know about defragging computers? All right, cool. So basically the reason why you defrag is because you have basically poor usage of your memory on your hard drive, which if you're using a solid state drive, you don't need to worry about that. Thank God for technology. Basically what it means is that sometimes when you're trying to store stuff on your disk, if things are fragmented, you might store like one section of a program in one location and another section in a very far away location. If you need to jump back and forth between those two, imagine you're doing a for loop and like half of the for loop is stored in like address like 0 and the other half of the for loop is stored in like address 1 billion, then you need to like read back and forth between those two sections really quickly, and that's what causes sometimes issues for your computer to slow down if you have a very full hard drive. If your memory gets too fragmented, and you basically need to link your program across different parts of your hard drive, and it can be very problematic. So this is why linked data structures is actually both a good and a bad thing. So someone was saying, does it help with quicker access? And the answer is no. So when you're accessing an array by default, what do you think the time is to access any one particular element? Let's just talk about that now. We're going to go over a little bit of theory. So with the standard array, non-linked array, time to look up / change a value. I can spell. So what's the runtime? In the standard array. I saw someone had a hand up over here. Dylan? Bueller? Okay. Yep.
Is it order 1?
Oh, it'd be order 1.
I don't know.
You don't know? It just sounds like you got an idea. Yeah, there's someone over there.
I mean, if the array is completely full and you're just accessing it because the block memory directly goes to it, so it's order 1, and if you have to add something, then you have to like go to the entire array.
So yeah, if you're changing a value from one value to another though, it should be order constant as well, right? Because if we're just like overwriting like a new thing, it should be order 1. And lookup, like you said, is order 1 as well. So yeah, in both of these cases, with the standard array, it'll be order 1 runtime. So it's going to be super quick with our regular array. And this is like using like int star. Now, this is for changing a value. This is not removing a value. If you wanted to remove a value, so what's going to be the runtime if you want to remove a value from an array? Yeah.
Order n.
Why is it order n?
Well, if the array is full, and depending on where you move it in the index, you would have to move all the values.
So this is a little bit of a trick question, I'm sorry. So it is order n in the average case, and it's order n in the worst case as well. But in the best case scenario, it could be order 1. And the reason why is because if you're at the very end of the array, and you want to remove the value, then you don't need to rearrange any of the positions. You just basically remove that value from the array, and you basically reduce the size somehow of your array. So if you remove a random value in the array, like if it's uniformly distributed across the array, like index-wise, it's going to be order n. And I can go ahead and do a real quick proof over why it would be order n to do a removal. So the reason why it's order n to do a removal is because when you remove a value, so it's order n. When you remove a value, basically we're assuming it's randomly distributed. The index is from a random, uniformly random distribution. Let me fix that a little bit. index from uniform random, why did I write it over there? Uniform random distribution. And that means I'm going to say that each spot is basically equally likely to be chosen. That's what the uniform random means. So that means the first spot in the array, so spot 1, has a 1 in n chance where n is the size of the array. Spot 2 has a 1 in n chance where n is the size of the array. Spot 3 has a 1 in n chance where n is the size of the array. Spot n has a 1 in n chance. And so the idea is if we remove a value from an array, what we need to do is we need to go to all the values after it, and we need to move it down 1. So how many values do we need to move down if we remove from the first spot in the array? Yeah, we need to move down n minus 1 elements. So move down elements. At 1, it's going to be n minus 1 different values, because the idea is if we're moving from the first spot in the array, then every other spot needs to move. So I could probably write like this as a table. All right, so then what's spot 2? How many elements do I need to move if it's at spot 2? It's going to be n minus 2 because we have one less element that we have to move down. So then in spot 3, what is it? N minus 3. Yeah, it's just really easy, right? It's just n minus whatever the value up above is. And so here, what's at spot n then? Yeah, n minus n, which is going to be 0. All right, so then what's the expected value? Hopefully you guys know expected values. No? Well, that's going to be a shame. So what's the expected number of moves given this setup? What? Yeah, it's the weighted mean. So the weighted mean would be... No, so in the general case, for a size of n, for size n array, technically I use lowercase n above, but we're going to go ahead and do that here. Lowercase here. So, you guys know expected value, right? Raise your hand if you don't know expected values. Ooh, rough. All right, so yeah, that's great. So how expected values work? So like I learned it in high school, like in algebra, but I don't know. I had like weird curriculum because I'm from like the 70s or something. I don't know. So the expected value is always the sum of the probability of each event occurring. You can imagine p of x times whatever the value of x is, effectively. And so the probability of x occurring inside spot 1 is 1 over n, and then the value of it is n minus 1. And then it will be plus the summation of 1 over n times n minus 2, plus 1 over n times n minus 3, 1 over n times n minus n. So it's going to turn into, in our case, the summation of I equals 1 to n of n minus I times 1 over n. Because 1 over n is the probability. I like swap these two because I'm the nerd. And we end up getting this formula. So you guys have worked with summations before, right? This should be something nice for you to solve, right? So what do? It's good practice. Use those things that you did in the exam, hopefully. Substitute n for I. Oh, okay. Yeah, so we'll do that eventually, but the thing is we don't have it at that form yet. We need to go ahead and do our reductions on summations first. So the reductions on summations, we can go ahead and pull out a 1 over n factor. So this is going to be I equals 1 to n of 1 over n times n minus I. And then we're going to go ahead and split this up. And it's going to be 1 over n times n minus the summation of I equals 1 to n of I. And now hopefully you guys recognize this form a little bit. Hopefully. So what this is going to turn into is 1 over n times, this is just n times n. Do you guys agree? Is there anyone that's lost so far? Raise your hand if you're not following this logic. Okay, I guess everyone's good. What's this section going to be? Minus what? N squared? Testing you guys. All right. So now what do we have? Can we do something with this? Hopefully. Oh, we can pull an n out, sort of. Yeah. So you can pull an n out. This is n over n times n minus n plus 1 over 2. And so this is just going to be 1 times n minus, I'm going to go ahead and say this is 2n over 2 minus n plus 1 over 2, which is 1 times n minus 1 over 2. And what is this equal to? Is that right? What's the big O of this, though? Yeah, this is order n. And the reason why is because we drop the constants and get rid of non-dominant terms. This is non-dominant. And this is a constant factor. So removal from a regular array is going to be order n on the average case, is what I just showed. In the worst case scenario, what is it? In the worst case scenario, we actually wrote it out. So, all right. So it's not that it's slow per se, because slow is like in the eye of the beholder, I guess, or something like that. It's not fast though. So there's a question here. Oh yeah, I'll do that. All right. So I'll go ahead and leave this here for a little bit, and I'll begin talking about what we're going to do now. So what we're going to do is we're going to go ahead and try to write a structure, and we're going to try to have that structure be linked. We're going to write it at code on paper, and then hopefully by the end of class I'll feel confident enough to code it in front of you guys, and we can go ahead and do some analysis on that. I mean, I'm confident enough to code it right now, but I kind of want to talk you through it so that way you guys understand where we're going to be trying to go. All right. So if we're going to be making a data structure, and the idea of this data structure is that I'll go over a proof for how bad it is later. So we're going to go ahead and make this linked data structure. And storing the three guys that I was talking about here, that's a little bit tough. And so instead what I'm going to do is I'm going to make this even easier on myself. And rather than storing it like this, I'm going to go ahead and store it where it's just one element that points to somewhere else. So that way it keeps my structure very small. Because if I did the other way, I could do it. Maybe I should do it both ways. That sounds horrible. All right. So if we're going to do it the first way, what we would have is we'd have in code struct. We'll call it like linked element. And now it's going to store inside the original one. It had int, whatever the first guy was. So we're going to call it first, int second, and int third. And so that takes care of these three guys that I have here. This is my first element, this is my second element, and this is my third element. And now what I need to do is, in my data structure, is I need to have some way of, referring to myself somewhere else. I need to basically store, like, what? Yeah, I need to store a pointer to myself, or like a data structure that's similar to me. So what I'm going to do for my last guy here inside this structure is I'm just going to go ahead and make a struct called, it's a struct of linked element. And it needs to be a pointer. And it's going to point to basically the next guy. And so this is what it's going to look like in code when I try to make this linked data structure. Now this could be a little bit more complex. And how much more complex could it be is probably what you're going to be asking. But it could be really horrible. So this is like really nice if I was just trying to store 3 integers. But I could also link together other more horrible things. Like I could link not only just these integers, but I could link like characters, or I could link like other data structures. And other data structures can include stuff like integer arrays, or even string array, or character arrays, which are strings. So you can have like really crazy stuff going on in here. And not only that, but it doesn't need to be just one type. It can also be multiple. I can mix and match depending on what I need to be storing inside these linked data structures. So if I needed to store like first, second, and third as integers, that's great. But maybe I wanted to store some like student information. Like remember we were doing an example of the labs with the students where we had their names, we had maybe their grades or something like that. I have no clue what examples you've done inside the labs now that I think about it. Oh, you guys did an author example, right? So yeah, so imagine you wanted to store these authors and you wanted to store them in this linked data structure. You can very easily store all the author information inside one of these linked data structures, and that would be like really messy. I don't really like doing that. Instead, what I like to do if I need to do one of these linked data structures, I need to have like very complex values. Instead of storing it this way, I actually store it as slightly different. So this is like nice to go ahead and get yourself started and introduced into the concept. It's a good start. But we're going to go ahead and do something a little bit better. Hopefully. All right. So instead what we're going to be doing, if we only need to do like a linear, a sequential list of values, what we can instead do we can go ahead and have like basically what's known as a wrapper. And I'm not talking about M&M. I'm talking about something you have in candy and you eat. I am too busy to unwrap the candy before we get. So what the wrapper is going to do is it's basically going to try to encapsulate what we're trying to store by basically providing an extra level of indirection or an extra level of abstraction, which you don't really need to know what those means because you haven't taken object-oriented programming. But the idea is that we want this to basically be a high-level structure that kind of points to where I want to go to. Because it would be very difficult sometimes to create an entirely new object if I want to like potentially copy values over or replace them. It would be much easier to just go ahead and work with the complex data structure. So you can imagine if I want to go ahead and store some author information, so I want to like maybe use some struct that's an author type. And this is like a really horrible data structure. It's got a lot of things in it. I forgot the semicolon, it's super important. All right, so this is like a really big data structure, and I want to be able to keep these in a linked list, but the issue is I don't want to make an author that is specifically a linked author list. I want to be able to use the author without the linked behavior. So what I'm going to do is in my wrapper struct, what I'm going to have is something that points to an author. So I'm going to have a struct author star, and what this is going to be is my reference author. And now inside this wrapper, what I'm going to have additionally is I'm going to have the ability to do a struct wrapper star, and this is going to be the next wrapper, or the next guy. Now, if you understand what's going on here, like completely, I'm one, impressed, and two, you're probably like fascinated. It's like, wow, this is a really interesting way of storing this. And for like the 98% of you that are not in that group, that's okay. We'll go ahead and go over this a little bit. So what we're trying to do now is we don't want to actually have like all this author information, like have an extra thing that allows us to point to new guys, because that would be crazy. Instead, what we want to do is we want to go ahead and just keep the author the same information. We don't really want to edit it, and we want to just be able to go ahead and point to the authors instead from our list rather than having to create like this extra author, like make a new structure and probably do something really horrible and dangerous. It allows you to very easily refactor code. So I don't like this. The previous one was kind of like that. We have like all this extra information and then we have a link to the next guy, which is what this is kind of doing. It's all this extra information and then a link to the next guy. Instead, all our data structure looks like a wrapper is just 2 pointers. One pointer points to some author and the other pointer points to the next guy in our list. And now you're cooking with pointers, or coding with pointers? I don't know. So it's just like something really simple. Our data structures are very easy to draw, as long as you're like not paying attention to what's going on down here. Basically, you can imagine that this is author 1, this is author 2, this will be author 3. And the one thing that's really nice about this is if you wanted to, with this data structure, is you can do some funny stuff where you go ahead and maybe have the wrapper point to potentially the same author twice in a row. And you wouldn't be able to do that with the other structure very easily. And the reason why it would be difficult to do that with the other structure is because having it point to the same author twice in a row might end up causing a cycle inside your chain of values. And having a cycle in your chain of values might make it so that we can never figure out where the end is. The nice part about this is if you have this type of data structure, you can find out where the end of your list is by just figuring out where your null is pointing at. As soon as you point to null, you know this guy has to be the last element in your data, in your chain. So is there anyone that's lost or confused as to what's going on with this example? Please raise your hand if you have any questions. Yeah.
So my question is, you basically have a struct that's pointing to another struct.
Yep. And okay, so I'll go with you because I saw you.
At least if I'm using Java wrappers, you have the primary data type, and you are trying to hide it or change it to another data type.
Yeah, so we're doing that. The wrapper is, so the primary data type is author, and then we're using the wrapper to kind of like point to it like indirectly. And then that allows us to very easily like encapsulate that data without like doing much. And like you get a lot of extra behavior by doing this as well. Because you're having these pointers, you could have like in like really weird situations. This is like just like I don't know like what you would want to think of this as. We can have like this guy points to author 1. And then you could potentially have this guy point to author 1 as well, which is something I mentioned. And then you could have the list continue. And the reason why this is interesting that you can do it in this list and not the other list is because in the other list, if you wanted to have, so imagine you have this author 1, and it points to author 2, which points to author 3. If you wanted author 1 to occur twice in a row in your list, what you might be tempted to do is just to go ahead and take this pointer and point it to itself. So go ahead and try to avoid having it point to author 2. But the issue is if you have this pointer point to itself, then that means when you follow this pointer, you end up here, back at the same place you started. And then when you follow the pointer, you end up back at the same place you started again. And you'll basically end up in an infinite loop, and that will create a problem. And so you can't easily make it so author 1 occurs twice in the list without taking all the values in this huge data structure and changing them to whatever author 1 was. And that would take a very long time. Well, changing just the value of an address is very quick and see. And so that's why doing these wrappers can sometimes help save time with doing a lot of writing. It won't be necessary for the homework though, because the homework I think is going to be like small enough values where you can go ahead and change all the values and there won't be any issue. And I don't even think I asked you to do anything crazy manipulation-wise with changing things, like changing what something's pointing to unless you're actually inserting something or removing something on the stack, which is something we'll hopefully be able to cover soon. So yeah, what's your question now?
Can you scroll back up then?
Yeah. So
So you have a variable called next guy that's pointing to the struct wrapper, right?
Yeah.
And so, and you have author that points to the struct author. Now, how does that translate to that diagram you got right there?
Which value? This one here?
Yeah, like how does that translate to that?
So this here is a wrapper. And so is this thing here and this thing here. So all these are wrappers. And now the wrappers have the ability to point to an author, which is known as the reference author. And that's what this box is here, what it represents. That box, the first box in all these little wrappers, is the reference author pointer. And the second box in all these little wrappers is the wrapper reference, which is the next guy. So like each one of these wrappers has two values. Both of them are pointers. And so each one of these wrappers has two values, two things inside the box, and they're both pointers. One is pointing to an author, and the other one is pointing to another wrapper. So question? You could. You could have really fun structures where you have something like reference author 1 and reference author 2. And then you can make it so that way each wrapper points to two different people. Like maybe you have even worse, I wouldn't want to say worse, but imagine you have like a collection of authors that you want to group up or something like that. And so maybe instead of having a wrapper per se, but you have like a discipline study. So maybe there's like a group of authors that are computer science writers. Maybe you have a group of authors that are mathematician writers. Then in your mathematician and computer science, you have some overlap. And so you can have like basically arrays of these guys that point into the same authors at these different locations. And so you can all reference that same memory. And it would be good to do that with this wrapper structure because the thing is you wouldn't want potentially this computer science to reference a mathematician if you want to be in a computer science array. And so that's why the wrapper is very useful, is because it allows you to avoid having issues where you're pointing out of order. And so I just encourage you guys, if you go into the workforce where you're doing computer science, is to use something like this rather than trying to modify your author data to look something like this here. This is very bad practice. Question here? So the idea is like if we had all the author information stored like sequentially, it'd be very difficult to do that. And not only that, but if I wanted to add one author to my list of values and I needed to reallocate, that could be really slow allocating a large section of memory. But if I need to add just an author to this list, I just need to make one new author if it's using a linked data structure. Because I just make one new author, I find the end of the list and I have it point to that next guy. And that can like save us a lot of time with doing allocation, and it makes it so that we don't have to worry about too much about resource management and like where things are being stored at in memory. So it helps with data locality as well, a little bit. You can sometimes end up being penalized because the idea is if your stuff is too fragmented, then like you could be jumping all across your memory and causing like crashing behavior, and that's not good. But we won't care about that in class. We'll care about that in computer architecture and a few other courses. So there's a lot more questions. I saw you for a while, so I'm really sorry. Let's get to you.
How much? God.
Yeah, me too.
How much would C? Good God. How much would C hate you if you like instead of calling struct, like instead of like saying like struct wrapper, like if you declared it at the very end of it as just wrapper, would it not read that at the end? But if you didn't put struct, it would just like shit out on you.
I don't really like to test C.
Okay.
I understand that's very
So just
difficult.
be safe and say struct in
You
front
can
of the
try
stuff,
it out.
right?
I recommend doing it on your own. It's great something to go ahead and check to see what happens, play around with it. I'll actually try it out in class, and we'll go ahead and see how horrible crash and burns, okay?
Thank you.
It might not crash and burn. Yeah, I need water too. All right, I saw you first, and then I'll get you, okay? So just hold on for a moment. Yeah, that's hard. So it requires linear operations because the idea, average case linear, because the idea is you have to look at the first author. You're like, no, that's not the person I want. So you look at the next author. No, that's not the person I want. You look at the next author. No, that's not the person I want. Even if the data is sorted, like hypothetically, if we knew like the authors are sorted by last name. In the regular list, to find out where the author's at, we can binary search, right? We don't have the ability to binary search here because we don't know where author 3 is at. We only know potentially where the first author is. And so we go to where the first author is, and then we go ahead and use that to go to where the second author is. And then we have to use that to go to where the third author is. And so if you're trying to find some guy in a sorted linked list, it's actually still slow. But in a regular list where in the regular array where everything was stored in a sequence, it was very easy to find everything. So yes, there are problems with doing the finding of the third author. Yeah, another question? Yeah, so we're going to talk about how to remove from these things safely. That's hopefully something I'll be able to cover by the end of class. But that is something that's really hard. It's hard to do initially, and it's not as bad once you've seen it a few times. Yeah, question? Oh, I'm sorry. I'll go ahead and do him first. If you still have one, I'll go ahead and get you. So what's up?
So, can you turn author one into a wrapper for this book?
Yeah, actually, you can go ahead and do that kind of stuff as well. You can go ahead and make author one kind of be a wrapper for a book. You can also make books be wrappers for authors, or you can just have like them pointing to each other. And so as long as you have like references from authors to books and from books to authors, you can go ahead and do however many connections you want to do. So that's like a good idea, and it would be a fun thing to try out. Although we're not going to be doing that in the lab. Instead, we're going to be working with friends, and we're going to be working with linked structures in the lab that way. So we're going back to friend examples. Isn't that great? All right, is there any other questions before I move on? I know that there's like a lot of stuff on this because it's kind of a new topic for a lot of you guys. All right, so someone mentioned something very important, which is, what if I wanted to remove one of my authors from this list? What if I wanted to remove like author 2, hypothetically? So if I wanted to remove author 2, what you might be tempted to do is say, okay, author 1, you're not going to be pointing to author 2 anymore. We're going to go ahead and free author 2, and we're going to point to null. So what someone pointed out, though, is if we went ahead and freed author 2 and then had author 1 point to null, is the memory that we freed, it's like kind of grayed out now. This guy here was pointing to something that we ended up not removing, author 3. And so if we remove author 3, this could be very damaging. I mean, if author 2 was the last person in my list, do you guys agree that this would have worked just fine? Why would this have worked just fine if author 2 was the last element in my list? Yeah, he points to null already, right? We don't have to worry about freeing null because null doesn't need to be freed. Like, we're good with the structure. If we remove on the end of the list, there's no problem at all. So what can we do to potentially circumvent this issue? Yeah, we have author 1 just point to whoever the author 2 is pointing to. So before we remove author 2, what we do is we just say, author 1, you're going to go ahead and point to whoever author 2 is pointing to. That's a lot of 2's. All right, let's go ahead and draw that out pictorially. So we want to remove this guy here. We don't really care how far this ends up going. You could keep going for a long time. So what we're going to do, what's been suggested, is we go ahead and take this pointer guy and just point it to the next element over. And then we're good, right? Oh yeah, free author 2. So we should free author 2 and then we change the pointer, right? No. Well, it sounds like neither one of these solutions are working, so we can't do this problem anymore. It's too hard. We'll just take the F on the exam or something, I don't know. Woo! Yeah, here.
We copy the pointer value for the third element out of the second element into something temporary,
Yeah.
and then reassign and free the second one.
Okay, that's good. So what we're going to do is we're going to create a temporary, this was a bad idea. Don't do that. We're going to create a temporary pointer. And that's going to go ahead and point to where we need to go to. I love drawing boxes. All right. So we're going to create this temporary pointer. It's going to point to where we need to go to. And it's going to basically be, we're going to take the guy we're going to delete. We're going to go ahead and say, all right, the next element is what we need to get to. And now we're free to delete this guy. And so now when we delete this guy is gone now. Oop. And what we can do is we can go ahead and update the pointer. So step one is we grab the temporary pointer. Step two is we kill this guy. Not really, we're not Russia or something like that. I'm kidding. That's a harsh word. Free. Free sounds so much better, right? It's liberating. Like, computer scientists are actually vindictive people, and then they just have to rename things so that way they don't sound as horrible. All right, and then what we do is we need to update this pointer at the end. For step 3. And so, how are we gonna update this? Yeah, we just have to point to whatever temp's pointing to. So I know that sounds really weird, and you're probably gonna look at the code and you're gonna be like, this can't be right. But it's actually not that bad to do. Let's go ahead and code it up. Code it up. Code it up. Any moment now? Okay, there we go. It's okay. I know that it's not there right now. I'm just trying to get to the directory. Is this week 6 or 7?
7.
There's no way. All right. Clear. And then, oh, I should probably open up my Notepad++. Make sure there's nothing crazy going on there. All right. Goes all to the left and not this left. All right. That's not right. That's almost there. Closer. All right. It's been a long day. First line. All right. That's going to be rough. All right. We can do this. All right. So we should always include the standard lib, standard I/O. Those are always very useful, especially in this class because we need to use dynamic memory. We have some main function. It's going to go ahead and return exit success. So some people were like, you shouldn't return an exit success, you should return an exit failure. And I'm like, I didn't think the program did that poorly to merit that, but okay. Thank you for that, if you said that. It made me feel terrible. All right. Now what we're going to do is we're going to go ahead and just kind of create a joke delete function. But we need to create the structure first. So struct. It's too difficult to work with authors with the short amount of time we have. So instead of doing authors, I'm going to do instead just integers, because integers is like reasonable, and they're not horrible to allocate things for. So we're going to just do a very simple linked list where it's just going to be an integer that points to another integer thing. So this is going to not be called a wrapper. I'm just going to call this an element. That's too generic. A node. Also very generic. Thing. That's specific enough. All right. There's going to be a value, and then we're going to have a strict thing star next. And so now what I'm going to do is I'm going to have a first thing. So struct you know what I should do? I should, 1, put a semicolon at the end of my structure, 2, put the word thing here, because the third thing I need to do is I want to type up this and not have to type struct thing every single time. So this is going to be a thing star, and this is going to be the first element. And so the first element is initially what? No, yeah, there's nothing in my list. So really, if I want to be like super cautious, super pedantic, whatever you want to call that, I'm going to say first element is equal to null. In other words, the pointer to the first thing is going to be null. I don't have to worry about it. If I want to go ahead and create a value, let's go ahead and do that. So we're going to go ahead and create value, or create thing. It's terrible. All right, we're going to go to value 6. And we're going to go ahead and make a function that makes a thing for us. I should have called this widget instead, because this is going to be way too confusing. I'll probably refactor this at the end before I submit it, if I can remember. So create thing, it's going to take in an integer, and that's all it's going to do. And now we're going to go ahead and create the method for creating the structure. So thing int value. And now this is going to go ahead and return some created thing. Let's see if anyone knows how to do this. So I want to go ahead and create a thing here. Literally, I know that's like kind of confusing. But how do I create a thing? How do I create and return one? Yeah? Oh. So how do I create a thing? A widget? A gizmo? Gizmo would have been a good word. I love gremlins. Okay, no one watches gremlins. Good to know. Yeah?
We should be able to reference the value and the next item.
Yeah, so we need both the value and the next item, technically. We won't really worry too much about the being passed in the next item. You know what? Why not? We can do that. That might make it easier if I can type next item. Items would have been a good word for this. All right, so thing star. When I need to do those, I need to create this guy. And so I'm going to go ahead and use calc. And then I'm going to go ahead and make it be the size of the thing data type. Or the thing object element struct. How many of these am I creating? 1. So there's only going to be 1 of these. And now what I can do is I can go ahead and very easily say, well, first of all, I need to check if this is null, or it's safe to check if it's null. So if ret is equal to null, then bad stuff happened. I'm just going to go ahead and return ret. Why don't I need to breathe before returning ret? No. So this is checking to see if we failed the allocation. Check for failed allocation. So the thing is, if you fail to allocate the value, then that means your value hasn't been created yet. And so all you need to do is just say, hey, you weren't able to create any memory. You don't actually need to free anything because nothing has been created by this point. So you just go ahead and check if the value is null, because that's what you return when calc fails. You just go ahead and return the value because you're returning null, saying, hey, I wasn't able to create something, be aware of this. Hopefully everything works out. If it doesn't, then that's going to be an issue. So otherwise, ret has been successfully allocated. So we can go ahead and set the value of ret is equal to the value we have. And then what we can say is ret's next is equal to the next item. And now we're going to go ahead and return the created value. And this is to just go ahead and initialize Alright, so this is all you need to do the creation of these elements. It might seem like a lot, but it's really not. It's really 1, 2, 3, 4 major lines of code. If I wanted to, I could have made this a lot shorter. I didn't need to do the check for the failed allocation, but it's a good practice to have if you're doing C coding. Oh my god, where'd the time go? Alright, so what I'm going to do is I'm going to say the first element is equal to create thing. And now I'm going to go ahead and add some more elements to this. I'm going to go ahead and actually, instead of doing 6, I'm going to do 7. And I'm going to go ahead and just create the elements that I have written on my piece of paper. They were 7, 3, 4, 2, 1, 5, 5, 9. So I know that you guys probably didn't catch all that. I'll create a comment here. So 7, 3, 4, 2, 1, 5, 5, and 9. So to link these up, if I just want to go ahead and insert them in order, what I can do is I can just go ahead and say the first element is equal to create thing, which I should really do 7 comma the first element here, because I need to add it to the list of elements. I need to go ahead and make sure the next guy is hooked up properly. 1, I need to go ahead and pass in the thing star here, because that's what the function requires now, because I'm passing in the next item now. And 2, I want to make sure that it's going into my list properly. And so this will do this. Now, this is not going to work, unfortunately, for several reasons. I'm going to go ahead and fix one of them if I can, but I probably won't have enough time. So this is going to be 3, 4, 2, 1, 5, 5, and I cannot count today. Ooh, close. 9. So now I have all the values in there. I'm going to go ahead and just do a quick print. And it's going to take in the first element. And I need to make sure that this takes in a thing star. And now I'm going to have the void print method here take in a thing star. And all it's going to do is it's going to run through all the elements in the list and print them out. So while start, this is going to be hilarious, does not equal null. I don't know what I did there with that tabbing. Printf, %d, arrow, comma, this is going to be start arrow value. And then start is equal to start dash next. And I'm going to go ahead and for posterity or something, I'm going to go ahead and print out a new line. And I'm going to go ahead and say null. And I just totally did a Java thing. Alright, there we go. So assignment 3, that's CS2, so I don't really care. What are all these things? I don't want them to be in there. This is CS1, this is code, this is week 7, and I don't even know what to call this. Linked things. .c. Sounds legit. Alright, so now I should be able to not compile this properly because I didn't do my prototype for the print function. You thought you were going to get me, guys, but I got you instead. And I'm going to go ahead and just print out the item list twice to show that I'm not modifying it in between runs. I'm going to print an extra new line between them so that way you can see them being separated. So GCC, I really forgot what I called this, and unfortunately I hit tab, which causes my thing to freak out. Oh my god. I don't like this. I know it's not going to work though. So, can you guys tell me what's wrong with this list? It's backwards. Why is it? Yeah, why is it backwards? I did not put it in backwards. You guys saw me insert it in the right order. No? I kept adding it to the beginning instead of adding it to the end. Ugh. Okay. I'm doing it? What am I doing? What am I doing? So what I'm going to do is I'm going to go ahead and have a last element instead. Oh man, that's going to be way too hard. So instead I'm going to do the dirty fix to it, and this is the dirty fix.
Oof.
And this is all you have to do in code when you want to reverse your list. Oh, you're right. Oh, I placed it in the wrong section there. Let me fix that. All right, there we go. All right, so now let's go ahead and... Okay, cool. And so now I have this really nice linked data structure that I can print the data structure out. I'm sorry I wasn't able to get to deletion. I'll try to cover that at the beginning of next class, so that way you guys can all see that working out in a very nice manner. I don't want to hold you guys up too late, because I know some of you guys have busy schedules.